So, in this session we are going to discuss about the mass transfer through an interface, and in majority of the cases the one of the phase will be gas and another will be liquid, right. So, definitely that does not mean that the discussion is only restricted to gas and liquid phases only. We can think of two liquid phases, that is in liquid-liquid extraction, also between the solid phase and the liquid phase, that is in leaching and also in drying. So, you see majorly we will be focusing on the gas liquid contacts and the respective interface mass transfer. So, what are the different steps? You see that if I think of an interface between a gas and the liquid, and let us think that the gas here we have two components A and B, and here in the liquid it is C and A, right. So, B and C in majority of the cases they are immiscible, right. So, these B here we will refer as carrier, here C is also the carrier, where A, the solute, will be transferred from either the gas phase to liquid phase. So, if A is transferred from gas to liquid, this is a typical case of absorption, right, and else if it is transferred from liquid to gas, it is stripping, right. Now, if both the phases are liquid phases, it may be liquid as well, right. So, then it is a typical liquid-liquid extraction. However, there these two carriers, they are partially miscible, which makes the thing relatively complicated. So, we will discuss it in due course. So, for the time being, let us consider that A, the solute, which is only getting transferred from this gas phase or to liquid phase or vice versa. So, what are the steps involved here? Which will be the diffusion of A from bulk gas phase to the interface. Now, you may think that why I am considering the diffusion, because very close to that interface it will be definitely diffusion, but far away in the bulk there will be convective transport, right. So, the second is absorption of A at the interface, which in most of the cases attains equilibrium. Third, diffusion of A from interface to bulk liquid. So, thing is that you see that the gas, this component A in the gas phase from the bulk, it will diffuse to the interface which requires a concentration gradient, right. So, at this interface it attains equilibrium, first it gets dissolved and it attains equilibrium, right. And this equilibrium is nearly instantaneous, okay. it needs basically a fraction of second. Why? Because the interface theoretically is a layer which is 2 to 3 molecular thick. So, its holding capacity of A is pretty small. So, once A reaches this interface with a definite finite concentration, immediately it saturates this interface and respectively and it attains equilibrium immediately, unless there is some interfacial resistance. And what are these interfacial resistance? Specifically, you see that for gas liquid contact, if I have surface active molecules, like the surface active molecules, if I have surface active molecules which are surfactants, so let me just narrate it down. Generally, it attains equilibrium within fraction of seconds. However, if we have surface active molecules in the system. Now, what are surface active molecules? Surface active molecules will have a long non-polar tail and a polar head, right. So, this is a polar head and non-polar tail. Or it may be some other type, specifically if it is this is, say, if this liquid is a non-polar carrier like some organic, then definitely the tail will be in this side, the head will pop out in the gas phase. Whereas the reverse will happen if I have an aqueous solution. The water being a polar solvent, the head will be here, the tail will be the gas phase. So, whenever we have surface active molecules, then the surface active molecules has a tendency to accumulate at that interface, and as a consequence it give rise to interfacial resistance, right. And then in those cases, the typical example of surface active molecules which we can commonly have is cetyl alcohol. So, it is a 10 carbon atom chain, and after that an OH group which is a polar group. So, that OH group is a polar head, and this long non-polar tail comprises of this carbon chain, right, this which has got number of carbon chiral centers around 10. So, that is a cetyl alcohol. Okay. So, those surface active molecules, they have got a tendency to accumulate at this interface, and based on whether the liquid is polar or non-polar, they will change the orientation of this head and tail, and will finally, no matter what is the orientation finally, it will give rise to an interfacial resistance, and in that case the interfacial equilibrium will be delayed, right. So, it will not attain the equilibrium instantaneously. So, anyway, so that is a rare case. Generally, it attains equilibrium within a fraction of second. However, if we have surface active molecules in the system, there will be a finite interfacial resistance which delays the process of attaining interfacial equilibrium. So, in general, the surface active molecules, it is a rare case in real life process plants. So, what we will have? We will have interfacial instantaneous equilibrium. So, this side we will have a concentration say YAI, and on this side we have a concentration XAI. So, these are the mole fraction. So, here this is YAI, here we will have let us say XAI. So, but remember that does not mean that XAI will be always below this YAI in that scale, it may be above. We will discuss when it will be above, when it will be below later, right. So, YAI will have the equilibrium relation. This is the equilibrium relation with XAI, right. So, that is the interfacial concentration. So, in case of ideal solution, we have the validity of Henry's law, that is YAI is equal to m into XAI, where m is the Henry's law constant. So, anyway, so definitely here YAI, and in the bulk the concentration of A or the mole fraction of A will be higher than that of interfacial concentration, because this A is to be transported from the bulk to the interface, which needs a driving force, and the pattern will be like this. So, this is YAG or YAG, that is the bulk gas mole fraction of A, and here we will have XAL, right. So, this XAL represents the bulk liquid phase mole fraction of A, right. So, you see that on these two sides, this will be the tentative profile of concentration or mole fraction, and this you see that why we will have a higher drop of concentration, because close to that interface we have this laminar sublayer, right. If both sides it is undergoing turbulence in the bulk, so close to that interface we have the laminar sublayer, and here it is quite evident that we will have the diffusive resistance, which is maximum. So, we need, if it is a steady state process, that here the rate of mass transfer and here the rate of mass transfer must be same, right. So, here we need a very low driving force, because the resistance is insignificantly lower as the Reynolds number towards bulk, local Reynolds number towards bulk increases, and we know from our previous discussion that the mass transfer coefficient has monotonically increasing trend with Reynolds number or the turbulence. So, here we need low driving force, here the driving force must be high. So, concentration change and the drop, the degree of concentration drop will be high. That means, here we will have high gradient of concentration close to that interface, and it simply decays down to a constant value of the bulk concentration at that bulk gas or the bulk liquid phase. So, based on this idea, we can think of two resistances on the two sides of that interface, which means we can apply the typical two film theory as proposed by Wittmann. So, we can think of two film theory which was proposed by Wittmann. So, just the film is, we can think the same as that of the film theory of mass transfer. We can think of this linear concentration profile, which is the tangent to the existing one at that interface, and here you see that there will be films, that gas side film and this is the liquid side film. Right? So, you see that if I fix a coordinate system like Z towards the bulk of the liquid, so this domain is Z negative, the gas side is Z negative and the liquid side is Z positive. The interface is located at Z equal to 0. So, we can write that limit Z tending to 0 minus Ya is Yai, and limit Z tends to 0 plus Xa is Xai, and they are in equilibrium with each other. Right? Now you see that as if we don't consider this a steady state kind of profile, and here the mass transfer from the bulk to the interface, right, even if it is an unsteady state, the mass transfer rate from the bulk to the interface must be same on the liquid side from the interface to the bulk. Why? Because the interface has got 0 mass, and that's why its material holding capacity is 0, right? So, there is no accumulation, no rate of accumulation at the interface. So, whatever comes to the interface must leave. Okay? So, from there we can say that as the area, it is a planar interface, as the area remains same. So, from in the gas side and in the liquid side. So, definitely the flux from the component A from the bulk gas to the interface must be same of this component, same component A in the liquid from the interface to the bulk. So, what we can write? We can write this Na is equal to Ky Yag minus Yai must be is equal to Kx into Xai minus Xal. Correct? So, naturally, it gives you an idea that how to measure this interfacial concentration, or how to determine rather the interfacial concentration, because see, with the help of analytical instrument we can measure the bulk phase concentration like Yag and Xal. These are measurable, right? But we cannot measure the concentration at the interface. So, that we have to estimate, provided we know this Kx and Ky. How we can do that? We will write that Yag minus Yai divided by Xal minus Xai is equal to minus of Kx by Ky. So, the point this Xal, Yag and Xai, Yai must be on a straight line with slope this minus of Kx by Ky. So, this can be graphically interpreted as here X and Y. Let us say this is the equilibrium line, which is Yai is some function, the equilibrium relation Xai, and we have located the point Xal and Yag, right. So, here for if the structure is like this, right, we have to understand that actually the gas phase mole fraction of A is higher than the liquid phase mole fraction. So, here we are thinking, if the point's location is here, we are thinking that the material A or the component A is being transferred from the gas phase to the liquid phase. On the contrary, if this point is on this side, right. So, here the gas phase this liquid phase concentration Xal is higher than Yag. So, we have to think that here actually the transfer is taking place from the liquid phase to the gas phase anyway. So, from this point which represents the bulk phase concentration. Let's write it as point B. If we drop a straight line with a slope is equal to minus of kx by ky, naturally it will be intersecting the equilibrium line as yai xai, because the interface must be at equilibrium. Okay? Right? So, with that basic understanding of how to determine the equilibrium concentration, now let us think very similar to this heat transfer. Let us think that, see, this kx and ky are the mass transfer coefficient, very similar to heat transfer coefficient. But we haven't, in heat transfer specifically discussing about the double pipe heat exchanger, we have introduced this idea of overall heat transfer coefficient capital U, right, which is in some way related to this HI and HO. So, similar to that, here we will try to think of an overall heat transfer, overall mass transfer coefficient, right, because the overall difference of concentration is YAG and here it is XAL. So, overall driving force is in the order of YAG minus XAL. However, we cannot write it like this. Why? Because they are not in the same basis. What is the basis here? Because you see, in heat transfer, we do not have to think about the basis, because this, if it is Tg, this is Ti, this is TL. At the interface, the profile is continuous. Here the profile is discontinuous. So, we have to either go by defining the overall driving force with respect to gas phase or with respect to the liquid phase. How we can define it? Here we have a discontinuity because of this equilibrium. Y and A are not of the same basis, that is why, right. So, if I think, if we replace, if we can write this equal to, if I write that YAG minus YAL star, right. YAL star is the gas phase concentration or gas phase mole fraction which is in equilibrium with bulk liquid, right. Or alternatively, we can write it as XAG star minus XAL, where this is the liquid phase concentration in equilibrium with bulk gas phase, right. So, we have to change the basis, and accordingly there are two different types of overall heat transfer, overall mass transfer coefficient. Overall mass transfer coefficient based on gas phase and overall mass transfer coefficient based on liquid phase, right. So, how we can write that? So, let us define first this overall mass transfer coefficient based on gas phase, right. We will write it as KOY. O stands for overall and Y indicates that this is based on the gas phase concentration. So, you see what is the respective driving force? YAG minus YAL star. So, we can write Na to be equal to KOY YAG minus YAL star. So, you see that Na divided by KOY equal to YAG minus YAL star. So, we will write YAG minus YAI plus YAI minus YAL star, right. So, this gives you that Na divided by KOY equal to by definition Na by small ky. We are trying to relate now the individual film mass transfer coefficient to the overall mass transfer coefficient. And here, if I think that this is the equilibrium relation is linear, m into xa, right. So, yai we can replace as m into xai and m into xal star, correct, sorry, xal, not xl star. So, this is Na divided by ky plus m Na divided by kx, because xai minus xal will be Na divided by kx. So, immediately we get 1 by koy is equal to 1 by small ky plus m by kx, right. Now, similarly, the overall mass transfer coefficient based on liquid phase, we have Na and this is KOX. So, Na is equal to KOX xag star minus xl. So, very similar to the previous analysis, Na divided by KOX is equal to, just see, xag star minus xai plus xai minus xal. So, this we can write as yag by m minus yai by m plus Na by kx. So, yag minus yai is equal to Na by ky. So, here we can write Na by kx plus 1 divided by m into ky, right. So, naturally, we have 1 divided by kox is equal to 1 by kx plus 1 by m into ky. So, this is the another relation based on this liquid phase, and this is for the gas phase. And from these two relations, we can get the idea of electrical network like resistance in series. So, here if I write yag, this will be yai and this will be ya star, yal star, and this will be 1 divided by ky and this is m divided by kx. And similarly, the other, here it is xag star, this is xai, this is xal. So, 1 by m into ky and here 1 by kx. However, what will happen if this equilibrium relation is non-linear? We have to locally linearize it. See, again we will draw this equilibrium relation, equilibrium curve, which is non-linear, right, and the respective line which a slope of minus of kx by ky. So, here it is xa, this is ya, this is a nonlinear equilibrium relation, ya is equal to phi of xa, and we have the point here, this is xal comma yag. So, we have dropped this line with a slope of, this line has got a slope of minus of kx by ky as we have discussed, and this is yai and this is xai, right. Now, you see that if I drop a perpendicular here, so this is in equilibrium with xal, so this is ya star, and on the other hand, if I extend this line, this is xal and this is xag star, right. Now, when we are looking for this 1 by KY, 1 by KY and m by Kx, right. You see that what are the respective driving forces? The total driving force is this one, YAG minus YA star, and that we are splitting into YAG minus YAI and next YAI to YA star. So, we are looking over this segment of this equilibrium line. So, and we have 2 points only. So, if I join these 2 points, I will get a slope say m prime. So, truly this relation will be m prime Kx. On the other hand, when we are looking for this sort of driving force, right, and we are breaking it down into two, this is the liquid phase actual, this is the gas phase hypothetical. We are looking for this segment of this equilibrium relation to transform this gas phase driving force in terms of liquid phase composition. So, actually we are looking for this segment, and respective linearization will yield slope m double prime. So, here we should use this m double prime truly, right, and we will get this sort of relation. So, this is m prime and this is m double prime in case of nonlinear equilibrium curve, right. So, once we have the idea of this electrical resistance, we can think definitely the one of the resistance may be negligibly small compared to the other, right. When it will be just like that. Okay. So, if I focus on this controlling resistance idea, which one is controlling? Idea of controlling resistance, right. Now, you see here m prime is low. What does it mean? It means that we have YA is equal to m prime into XA, right. Now, m prime low means XA must be very high, right. M prime low means XA must be very high, and multiplied by m prime, which is a low value, it is giving you YA, which is finite or moderate, right. M prime low means the component A is highly soluble in liquid, right. So, in that case, you see YAI will be here and XAI will be here, above and over. YAI is less than XAI. So, that is the implication of m prime low when the component is highly soluble. Just think that carbon dioxide in this ethanolamine or methanolamine, right. So, or secondary amines or tertiary amines wherever it is, whatever it is. So, carbon dioxide is highly soluble in amines like particularly alkyl amines. So, we have low value of m prime, the Henry's law constant or the Henry's law equivalent constant in case of nonlinear equilibrium relation. So, if m prime is low, component A is highly soluble in the liquid and our profile will change, XAI will be above and over this YAI. So, in that case 1 by KOI is nearly equal to 1 by KY. So, which means the gas phase resistance is controlling, right, provided you have low value of m prime. And what does it mean by controlling resistance? Here you see that actually 1 by capital K or 1 by small k represents the resistance. So, this resistance is majorly contributing plus some additional very small or insignificant liquid phase resistance as the gas is highly soluble. But we are not focusing on individual values of Ky and Kx, we are only thinking in terms of m, right. So, this is gas phase controlling resistance, Alternatively, we can think of liquid phase controlling resistance from the same formula without changing the equation. We don't have to go for the second one, right. So, this is case 1, and case 2 is M prime is high, right. So, as Ya is equal to M prime into Xa, okay, component A has low solubility in liquid, and we have this profile. This is Yai, M prime is high, so Xai must be lower than Yai. So, this is the profile, okay, tentatively. So, there 1 by KOI as M prime is high. So, this part is negligible, only this part will be counted. So, this is approximately equal to M prime by Kx. So, liquid phase resistance controlling. Controlling means this will basically dictate the overall resistance, and here in that case what will happen? Majorly, as the resistance is high, the rate of diffusion in the liquid phase will be low, right. Now, how we can improve this situation in real life? This is very, very important. This is a very basic understanding. You see, so far we have, in order to determine which one is the controlling resistance, we have only focused on M, not individually on Kx and Ky. Now, case 1, gas phase resistance controlling. So, try to improve. Obviously, we will try to increase Ky, right. So, if I am trying to increase Ky, definitely 1 by Ky will decrease and my overall convective rate of transfer will increase, right. So, how to increase Ky? Try to increase Ky. So, how to do that? Increase the Reynolds number of gas phase. Now, you see, whenever you are contacting, you are having a contact of the two phases, in industrial situations, we have to generate a huge interfacial area. So, definitely one of the phase must be dispersed in another phase, right. One of the phase must be dispersed in another phase. It may be gas dispersed in liquid or liquid dispersed in gas. So, typically you see, if a phase is dispersed, it is practically impossible to increase the internal Reynolds number within their drop or bubble, right. If here we want to increase the Reynolds number of the gas phase, so gas phase must be continuous, right. Gas phase must be a continuous phase, the liquid phase may be dispersed, right. So, increase of the Reynolds number of the gas phase. So, for that, first make the gas phase a continuous one, right, and then you can increase the velocity. And when the gas phase is continuous? In packed towers, because see, in packed towers what happens, we will discuss it in detail, the construction and all. We have a packing, it may be random packing, it may be a structured packing. Here we are delivering the liquid, right, the solvent or whatever, and liquid in, liquid out, L out. This is gas in, and here we have gas out. Now, whenever we are charging the liquid in this packed bed, so definitely the liquid will be forming the rivulets or dispersed drops, it will wet the surface and all, and through which the gas will be flowing upward, right. flowing upward. So gas phase is continuous. So if I have to make the gas phase continuous, so we have to use packed towers. Right. So this actually, why this is important, that if I have a high solubility of a component in which we want to transfer, that is a solute, in the liquid phase, that means the M prime is low, and which alternatively indicates the gas phase resistance will be controlling. So for an efficient operation in the respective mass exchanger, we have to increase the individual gas phase mass transfer coefficient Ky, and that can only be increased, we have seen that, if I increase the Reynolds number. So to increase the Reynolds number, we must generate the scope, and the scope is make the phase continuous, right? And whenever you are going for the gas phase continuous, the liquid phase must be dispersed, and the respective contacting pattern is only feasible in a packed bed, where it gives you continuous gas phase and dispersed liquid phase. And just the reverse happens in case if M prime is high. So case 2, liquid phase resistance is controlling. So obviously increase Kx, then make the liquid as continuous phase, and that the selection will be the tray column. Why? Because in tray column, you see, we have trays. It may be a sieve tray, it may be perforated, or it may be bubble cap, whatever it is. Here we have the downcomer, here we have the downcomer. The liquid actually forms a continuous cross flow streams and flows down to the downcomer at the opposite end, and the gas has to disperse through this liquid hold up in each tray, right? So this is a gas dispersed arrangement where the liquid is continuous. So if I have to increase the turbulence in the liquid phase internal to that specific phase, just like inside the bubble, it's pretty difficult to increase the turbulence, but we can increase this in liquid phase, right? Because it is continuous. So you have to go for tray column. And that is the reason, you see, in distillation and in different absorptions also, where we are using a solvent, though definitely it is a rare case, where we are using a solvent which has got and in which the solute has got a low solubility, right? Solute, if it has got a low solubility, then the liquid phase will be the controlling resistance, and mostly in distillation what happens, majorly the liquid phase, we will discuss it later, the liquid phase resistance is controlling. So mostly for these sort of operations we use tray column, whereas if the gas phase resistance is controlling, because here in absorption we intentionally select a solvent in which the component is highly soluble. So whenever it is highly soluble, the gas phase resistance is controlling, because the liquid phase resistance becomes insignificant as M prime is low. So in that case we have to go for packed towers. Okay? So that's the basic idea of this overall mass transfer resistance, and from there we can conclude about our device selection in which we are supposed to generate the contacts between the gas and the liquid phases. Okay? So with that idea of interfacial mass transfer or interfacial this separation techniques, let's now go for understanding the mass balance over a typical exchanger without specifying it's internal, like whether it is gas, whether it is a packed tower or a tray tower. Without specifying the internal, let's write the material balance over a mass exchanger, considering this entire thing as an envelope, right? And from there we will try to understand the idea of operating line. So, this is a material balance in a continuous equipment. Continuous mass exchanger. Right. Generally, we operate it in counter current mode. Sometimes we use cross current, but that we will not discuss right now. For standard these operations, it is always counter current. Like the liquid in, liquid is heavier, so it must be delivered from the top and withdrawn from the bottom. Whereas the gas being lighter than the liquid, here this will be the gas in and here it is the gas out. So, note that I have not specified what is the internal of this column, that it may be packed, it may be tray column. Now, how to represent the flow rate and the composition? So, let us consider a binary system, or rather at least only one of the component is being transferred. That is also the case. Only one component is being transferred from gas to liquid or vice versa. Right. So, how to represent the compositions and the flow rate? We can go for writing, let us say this side is, this end is 1, or let us not do it, let us write this side is 1, this side is 2.2. So, it is G1, Y1, this is L1, X1. So, this is L2, X2, this is G2, Y2, and any intermediate section, right, let us draw an envelope like this. So, here it is G, Y, here it is L, X, right. So, if I write the overall material balance, it's material balance, I should not say overall material balance over the whole device, right. So, if I go for the material balance over the whole device, what I will write? G1 Y1 minus G2 Y2 is equal to L1 X1 minus L2 X2, right. And this is a balance equation simply, no one is variable. But if I write it over the cascade, this, what I will get? G into Y minus G2 Y2 is equal to L into X minus L2 X2, where L, X, G, Y are variable, and what we can further write? Y is equal to L by G into X plus G2 Y2 minus L2 X2 divided by G, correct. So, this gives you an equation. What is the equation? What it relates? It relates at any section, it relates Y, which is the bulk gas phase composition, to X, which is liquid gas phase or liquid phase, bulk liquid phase composition, right. These two are being related through this equation, okay. And that is the equation of operating line, that how the concentration at any sectional point between these two counter current streams, how this concentration of the gas is related to that of liquid, and this is the operating line equation. Right? However, you have to understand that as there is a continuous transfer of A from this side to this side or from this side to this side, we do not know that. So, L and G, this are variable. Why? Because the total amount of liquid, the liquid's amount in terms of its components, right? One is the carrier liquid, another is the solute. And for the gas the same, one is the carrier gas, another is the solute. Just like the typical example, carbon dioxide plus air, and we are trying to remove carbon dioxide in an absorption tower where I am using tertiary amine, right, as my solvent. So initially, let us say the tertiary amine we are giving it, charging it in pure form. So X2 is 0, right? Now L2, what it contains? Only tertiary amine. And here the gas, it's air plus carbon dioxide. So air is a carrier, here tertiary amine is a carrier, in which the carbon dioxide has got a good solubility. So what will happen now? The carbon dioxide will be continuously abstracted from the gas phase and it goes on accumulating in the liquid phase. So L must increase as we move downward, whereas G must decrease as we move upward. So L and G are both variable, so this is a nonlinear equation. And this is the slope of this operating line is always, for all cases, it's the flow rate of the liquid to the flow rate of the gas. It's a ratio, right? That is the slope of this operating line. And here it is a variable slope. The intercept is also variable because G is variable. So this will give rise to a nonlinear operating line. So X and Y. And let's say this is the equilibrium line. YAI is equal to some function of XAI. There is a linear equilibrium relation, sorry, nonlinear equilibrium relation. And here if I can trace the operating line, I will get something like this, right? So it is a nonlinear operating line. And what are the points? If it is above the equilibrium line, which means the y for a given x, say it is x, so this is y and this is YAI, right, equilibrium, or let us write not YAI, let us write YA star, right. So YA star. So at this interface we can think that this YA star is lower than y and operating line is above and over the equilibrium line, which means the solute is getting transferred from the gas phase to the liquid phase. So this is the typical operating line for absorption. Alternatively, if I have the operating line here, then the YA star is higher than y, and essentially here the liquid is rich in terms of the component A, and that is getting transferred to the gas phase, just like similar to absorption of carbon dioxide and this air in the solvent of ethynylamine. So from the bottom you are getting carbon dioxide rich ethynylamine, but the ethynylamine is to be regenerated once again because it is to be used, and carbon dioxide you have to use for some other purpose. So what you will do? You feed it to another unit, right, where this liquid will be again delivered from the top, which is rich in carbon dioxide, and you charge steam, right, a steam from the bottom. The steam being the gas phase, it will strip the carbon dioxide into it, right, from the ethynylamine solution. So ethynylamine will be regenerated and we can again feed it back to the deabsorption column, and the steam plus carbon dioxide will feed to a condenser where the steam will condense to water and you will get the pure carbon dioxide. So this is the entire coupled process of absorption and stripping. So this is the operating line for absorption, where we have the transfer of the solute from gas to the liquid, and here this is the operating line for stripping, where we are delivering this same component from the liquid phase to the gas phase. So that's the relation between the equilibrium and operating line and the respective tentative measure of the driving force. Now the question exists that if the operating line itself is nonlinear, how to draw it, and whether it is possible to actually change the coordinate system to generate some linear operating line? Yes, it is possible. It's possible if I go for linear operating line. We use measures in solute free bases. Right, as I mentioned that only one component is being transferred. So, we'll write GS here. This is the carrier flow rate in gas phase. What is it? GS will be equal to G1 into 1 minus Y1. So, air flow rate from the bottom and the top will remain same. So, here also it is GS, right. And what will be the composition? How we can represent a composition? We can write Y1, which is the amount of A divided by amount of carrier. So, it is a kind of ratio, and that is Y1 divided by 1 minus Y1. So, capital Y1. So, here we can alternatively use GS and capital Y1. Here it will be GS and capital Y2. This similarly will be LS. LS is equal to L2 into 1 minus X2 and capital X2, which is small x2 divided by 1 minus x2. And similarly here LS, the LS remains unchanged, and here capital X1, which is X1 minus 1 minus X1. Now, in terms of that, what will be the operating line equation? So, operating line equation in terms of solute free basis measures. The overall balance will be LS into X1 minus X2 is equal to GS into Y1 minus Y2. And alternatively, it is the over this cascade the balance will be here. We will use this GS and Y, and here LS and X. So, LS into X minus X2 is equal to GS into Y minus Y2. So, you see this LS X minus X2 and GS Y minus Y2. Now, we have Y is equal to LS by GS into X plus GS into Y2 minus LS into X2 divided by GS. So, it is a straight line because GS and LS are fixed. So, in this solute free basis coordinate system, the equilibrium line may be nonlinear. That depends on the change relation, because we can change YA as capital Y divided by 1 plus Y, and here XA as capital X divided by 1 plus X, right. So, this is the new relation, say it is phi for phi 1, phi or phi S of X, and here we have the operating line, and the terminal points in the previous, this will have X2 and Y2, this will be having coordinates Y1 and X1. Here this will be capital Y2 and capital X2, this will be capital Y1 and capital X1, right. Now, it may be converted, it's converted to a linear operating line equation. Here the slope is LS by GS, which is constant, but here the slope is changing. Now, if it is stated that how to draw the operating line in the small x small y coordinate. So, that is pretty easy. We know these locations, and we will mark these 2 points, join them by a straight line, and we will draw the equilibrium line, and similar for the stripping, which will be on this other side, the operating line will be on the other side. Here, from this equation we cannot draw. So, how to draw the operating line for the small x small y coordinate? Actually, you see, we will consider the same relation, this one, right. So, it is GS into Y minus Y2 is equal to LS into X minus X2. Now, we will write, we will replace small y as small y, the capital Y as small y minus 1 minus y, and this is Y2, Y1 minus Y2 is equal to LS, this X divided by 1 minus X minus X2 divided by 1 minus X2. So for different values of x, now we can generate the values of y and we can draw this line. We can generate the points and join them by a smooth line. We can actually construct the nonlinear operating line in the small x, small y coordinate space. Okay? So that's the basic idea of the construction of operating line and equilibrium line, and we will see its utility in the next section what we are going to discuss. That let's now focus on a specific type of column, right? A specific type of column, and without going into the engineering details, let's see how a plate column or the tray tower functions. So in a plate column, as I have mentioned earlier, we have the number of plates which actually are trays which actually allow the contact of this gas and liquid, and the liquid is continuous where the gas is dispersed, and we must have the arrangement for the smooth delivery of liquid from one tray to another at its bottom. So typically it's a schematic, it's not the engineering details we are discussing about, it's the typical schematic. So here we have the liquid accumulated at the end. So we withdraw the liquid as Ls and X2, right. Here we charge the gas, and let us say it is a typical, it is a representation, it does not mean it is a sieve tray. This is a downcomer, and here we have something called bottom seal, right. So this downcomer will be on this side, if this is solid. Let me draw it first. Here we deliver the liquid. And from the top dome, we allow the outlet of the gas. Right. So let's use a break line here. And trays are counted generally from the top. So that is, here the liquid will flow into the downcomer. Here we have the gas bubbles exchanging mass. Right, from the downcomer, it will again flow into the downcomer opposite. Here we have the gas bubbles, here also the same thing. The same. And this is called the bottom seal. These are the trays or plates, or theoretically we call them stages, right, where we facilitate this exchange of mass between the gas and the liquid. So this is the downcomer or downtake, right. So liquid inlet nozzle, and this is the gas outlet, right, and this is the gas inlet nozzle. and here from we will have the liquid outlet nozzle. Okay. So, here the liquid will be LS and X0, YX0. This is the numbers are from top, N1, N2, N equal to capital N, right. So, in a stage or a tray, whatever gas leaves, if the stage is stage I, this will be Yi, this will be Xi, and this will be I plus 1. So, here obviously we will have Yi plus 1, here this will be Xi plus 1. So, obviously the whatever is coming is Xi minus 1. So, if it is stage 1, so the respective liquid composition is X0 and the gas outlet it will have Gs and Y1, here Ls and Xn, here the gas is Gs Yn plus 1 because the last tray is capital N, right. Now, here in this we can write what? We can write this overall balance as Gs into Yn plus 1 minus Y1 is equal to Ls into Xn minus X0, right. And for if I have this say it's a stage N. So let's use another break line here, and this is stage N. So if I have an envelope like this, right. So let's say it is envelope I, right. So balance over envelope I leads to the following equation. So, what will be the equation from the bottom? We have Yn plus 1, small n plus 1, next Y1 multiplied by Gs is equal to Ls Xn minus X0. So, we have the operating line equation as Yn plus 1 as Ls divided by Gs into Xn plus this Gs into Y1 minus Ls into X0 divided by Gs. So, again just like the previous, the operating line at any section, see at any section here this is Yn plus 1, here it is Xn. So, it is correlating these two composition, two bulk phase composition, one is Yn plus 1 and other is Xn. So, we have the operating line equation. So, it is capital X, capital Y, this is the equilibrium line, and let us say this is the operating line, right. Here we have this X0 and Y1, this is Yn plus 1 and Xn. Now, see we are starting from the top. At the top what we have? This is a tray, here we have Y1, here we have X0, here we have Y2, here we have X1. Now, Y1 and X1 they are in equilibrium, right. So, from Y1 if I extend this line like this, I will get X1. Now, from X1 if I move upward, right, keeping X1 same, if I move upward, the point where I intersect the operating line must be Y2 because operating line relates these two. So, this is Y2, right. So, once I just draw a stair, we were initially at these points. We have drawn a stair and we are going here. So, we have crossed a stage. So, one stair is equivalent to one stage, right, and this technique we can use to determine the number of stages. Just like if we repeat the process from y2, I will get x2, and if I move up, I will get y3. So, in this way we go on drawing the staircase, right, and finally here we are completing, and this staircase represents the ideal number of stages which are individual equilibrium stages, right. And this may be a fraction, because though the number of trays in a column is an integer, the number of equilibrium stages what we are determining by the staircase construction may be a fraction, because the actual plates or trays in a column may not lead to equilibrium between the outgoing gas stream and the outgoing liquid stream. However, when we are going for a theoretical calculation, how we can do that? See, this is 1, this is 2, this is 3, this is 4, and say this is a completion of single stage, and this length is say L1, where actually we have to go by L2. So, it is 4 plus L2 by L1, that is the number of theoretical stages we can determine in a plate column. So, that is the idea of number of stages determination by a graphical technique, and that was introduced by McCabe and Thiele, right. So, this is a brilliant idea. Otherwise, what you have to do? You have started from y1 and x0, right, because we know the terminal composition or terminal points of an operating line. So, y1 x0, that is the input, right. What you can do? Solve y is equal to phi s x with x equal to, or with y is equal to y1, and get x1, right. Use next, we will use the operating line equation. Use operating line equation to calculate y2, because from x1 we will get y2. Now, we have crossed a stage. So, in this way we will go down, right, and finally at yn theoretical, if it is greater than yn plus 1, which is the gas composition here, right. So, then we will stop and we will say that many number of equilibrium stages are needed actually to conduct this specific operation, where we will have an inlet gas at a composition of yn plus 1, an outlet is at y1, whereas the inlet liquid has a composition of x0. So, this is a tedious analytical calculation which has been many times, many-fold simplified in this graphical construction, right. So, this technique of analytical calculation, we will see that modified version in this distillation is called the Lewis-Sorel algorithm, or Lewis-Sorel technique of finding the number of stages in a distillation column. Distillation is much more complicated than this typical plate column, because there we have the feed from some intermediate point, right, and that has been simplified. This is called the modified, this approach, analytical approach is called the Lewis-Sorel technique, right, and that has been extremely simplified by the staircase construction in McCabe and Thiele. But we will see later in the next session, in the beginning of the next session, that if the equilibrium line is also linear, if the equilibrium line is also linear, we have a ready expression of this number of stages. We can do it even if they are not parallel, right. They may not be parallel, The equilibrium line is linear, the operating line must be linear in this capital X, capital Y coordinate space, and there we have an analytical expression of this, the necessary number of stages required to perform that given duty, and that is called the Kremser-Brown-Sorder equation. We will discuss about it in the next session. Thank you.